So I'm going to talk about digraph coloring. So the chromatic number of a digraph not containing some certain digraph, which is called two-block cycle. So first, a digraph coloring is a coloring of, actually digraph coloring is a coloring of its underlying graph. And the chromatic number of a digraph is the chromatic number of its underlying graph. So actually, if you want to color digraph, you need to color its underlying graph. Then why we study digraph coloring? Because it turns out that the chromatic number of a digraph gives very interesting information about its subdigraph. For example, this is a theorem of Galai and Roy. Actually, this is proved by Galai, Hasse, Roy, and Vitavio. This theorem says that if a digraph has a large chromatic number, then it contains a long directed path. Here, in this talk, the containment relation is subdigraph. Okay, so the theorem states that every digraph with chromatic number n is to n contains directed path with n vertices. And as an extension of this theorem, Adorio-Bori, Havet, and Tomase shows that this is true for two-block paths. Here, two-block path is an oriented path consisting of two maximal directed paths. Okay, so these two are examples of two-block paths with 5 vertices. Then maybe it's natural to ask if this is true for every oriented path, and it is a conjecture by Bondi. And as far as know, it's open. And next is the oriented tree, and there is a conjecture of Bart. He conjectures that every oriented tree with n vertices is contained in every every digraph with chromatic number n is to 2n minus 2. And in the same paper, he showed that this is true when the chromatic number is greater than or equal to n minus 1 squared. And later, Adorio-Bori, Havet, says, Reed, and Tomase shows that improved this result. So they prove that every digraph with chromatic number n is this contains every oriented tree with n vertices. Okay, the next is oriented cycle. Actually, the existence of graph with large chromatic number and large girth shows that this. For every oriented cycle C and every integer n, there exists a digraph D with a large chromatic number but not containing C. However, Bondi shows this. So if a strong digraph D has a large chromatic number, then it contains a subdivision of a directed cycle of a length n, which means that if a chromatic number is large, then it contains long cycle, directed cycle. Okay, then how can you extend this theorem? So Galai and Roy theorem is talking about directed path, and it is extended to two-block path. So maybe it's the right direction to ask if this is true for a two-block cycle. And actually, this question was raised by Adorio-Bori, Havet, Tomase. And yeah, they asked if every strong digraph D with large chromatic number contains a subdivision of C. So two-block cycle is just an oriented cycle consisting of two maximal directed paths like this. Okay, so now I'm gonna just focus on this question. So for convenience, from now on, we fix one two-block cycle C with n vertices, and we denote by Fc the set of all strong digraphs not containing C as not containing any subdivision of C. Okay, then this question is equivalent to that, because every strong digraph D not containing any subdivision of C have chromatic number n must n minus 1. And the first result of this question was by Cohen, Haber, Loche, and Nische, and they show that such a digraph D has chromatic number n most big O of n to the fourth. And actually, this is the first result to show that this digraph has bounded chromatic number. And last year, we improved this result. So we show that every strong digraph D not containing any subdivision of C has chromatic number n most 8 n squared. And so to prove this theorem, we need two lemmas. The first lemma is about the structure of a strong digraph D not containing C as not containing any subdivision of C. And the second lemma is about just coloring. So the first lemma states that every such D can be partitioned into x1, x2, xm such that the subdigraph induced by xi has a spanning cycle tree. And I'm going to define cycle tree later. And satisfying two properties in P1 and P2. And I'm going to state P1 and P2 later. So. And the digraph D prime obtained by contracting x1, x2, xm has no long cycle. So that is the first lemma. So it shows the structure of digraph D. And the second lemma says that if a strong digraph D has a spanning cycle tree T, so this spanning cycle tree satisfying two properties P1 and P2, then its chromatic number is bounded by 4n. So these conditions are equal to these conditions. So the second lemma says that every dxi has chromatic number n most 4n. And the second condition here, D prime doesn't contain a long cycle, which means that by Bond's theorem, the chromatic number of D prime is n most 2n. So these two lemmas directly prove the theorem. Okay. So suppose we have this partition, and by contracting x1 and x2 and x3, we obtain D. Okay, and the second lemma says that each part has chromatic number at most 4n. Oh yes, 4n. And Bond's theorem implies that D prime, the chromatic number of D prime, is n most 2n. So by combining these two colorings, we can prove that the chromatic number of D is n most 8n squared. Okay, now I'm going to show what cycle tree is. The cycle tree is just a digraph consisting of cycles. So it's just a union of directed cycles such that Ci shares only one vertex with the union of the previous these cycles. So just one directed cycle is a cycle tree, and we can construct cycle tree in this way. Okay. And we denote by Ct the set of all directed cycles. And similarly, we can define cycle path. So cycle path is a cycle tree having this form. So Ci and Cj meet if and only if I minus j is either 1 or minus 1. So only the consecutive cycles meet. That is a cycle path. this is not a cycle path because C2 and C4 meet. Okay. And cycle tree has tree-like properties. So for every tree, for every pair of vertices U and V, there is a unique path between them. Right? And cycle tree has similar properties. So for every ordered pair of vertices U and V, there is a unique path from U to V. And for every pair of cycles, directed cycles, there exists a unique cycle between them. And also he has a very nice property. So if we contract one cycle, it is still a cycle tree. And contracting one cycle doesn't break any other cycle. So the set of cycles is equal to just the set of cycles of T minus C. Yeah. Okay, now we know what cycle tree is. And now we are going to see how to partition VD into X1, X2, Xm such that this. Okay. Okay, we are going to construct sequence of digraphs D1, D2, Dk such that as follows. So we start with digraph D. So we set D1, D. And if Di is given, and we look at its longest cycle, and say this is Li, and if Li is long, so its length is n is 2n, then we contract Li to obtain Dni plus 1. And if Li is small, its length is less than 2n, then we stop this process and let Dk be the final digraph. So for example, so this is given D, and if it is the largest cycle and its length is n is 2n, then we contract and we obtain D2. And this is the largest in D2 and its length is greater than or equal to 2n, then we contract, and the length of largest cycle has a length less than 2n, then we stop. And this is the final digraph. Okay, now we'll just look at Dk and let the set of vertices of Dk be Vm to Vm. And because we obtain Dk by a series of contraction, actually Vk also obtained by Vi. Every vertex Vi is obtained by contracting some subset of vertices of D, right? So if we expand each vertex, we can go back to D, okay, and let Xi be the set of vertices by obtained by expanding Vi. Okay, and what I want to say is that here Dk and this partition X1, X2, X3 are actually what we are looking for here. Okay, so first D prime, because Dk doesn't contain long directed cycle. Okay, by the definition of by the process, we know that D prime contains no directed cycle of length greater than or equal to 2n. And also it turns out that each part has a spanning cycle tree Ti, where every cycle is actually comes from this set. Recall that Li is the largest, longest directed cycle in Dj, and we obtain Dj plus 1 by contracting Lj. Okay. Okay. So now we can fill out these two blanks. What is P1 and P2? So okay, every cycle tree here, for every cycle tree here, their cycles are long. Their length is n is 2n. So the first property is this. Every directed cycle of Ti has a length n is to n. And the second property is this. So here, L1 is the longest cycle indeed. And and Li is the longest cycle in Di. So it means that if you look at this part, L1 is the longest in X1. And if you contract L1, L3 is the longest. And if you contract L1 and L3, then L4 is the longest one. So we have this property. So there is a sequence of directed cycles of Ti such that Cj is a large directed cycle of Dxj, directed cycle of this digraph. Okay, actually, this lemma comes from this contracting and expanding process. Okay, now we're going to look at the second lemma. Okay, so second lemma says that for every strong digraph D contained in Fc, if D has a spanning cycle tree T satisfying the two properties P1 and P2, then its chromatic number is at most for n. Actually, you don't need to memorize what P1 and P2 because I'm not going to say it anymore. Okay, so let's first consider the simplest case. What is the simplest case? The simplest case is that T has only one directed cycle, which means that D contains a Hamiltonian directed cycle. In this case, actually, we can get a stronger result. Okay? Every Hamiltonian digraph D not containing any subdivision of C is n-1 degenerate. That is, its chromatic number is n most n. And this theorem will be used as a basic tool to prove this lemma. Okay, next we consider this case. T is a psychopath. Let's say the edges not contained in the same cycle is external. So here the red edges are external edges. If suppose there are no external edges, then sure we are happy because we color C1 because C1 itself is a Hamiltonian digraph. Using this theorem, we can color C1 with n colors. And then we color C2 and Cn-2, Cn-1, and so on. But of course, that's not true. I mean, there are tons of external edges. Then what if, suppose for every vertex V in Ci has n most 100 n neighbors in previous cycles. If that's true, then also we are happy because we can color vertices greedily. Starting with coloring C1 and C2, and when you color vertices in Ci, because it has almost 100 n neighbors in this part, and Ci is Dn-1 degenerate, we can color greedily. So actually, if that's true, then D is 1n degenerate. But but this assumption, of course, is not true. There are a lot of arbitrarily large number of neighbors of V in previous cycles. So it was hard part to how to handle these edges. And finally, we were able to find very magical set of external edges, such that we proved that there exists a set B of external edges, and which are called bad edges, such that first of all, B induces a bipart digraph, so its chromatic number is just 2. And if we remove B, then so here red edges are bad edges, and if we remove these bad edges, then we have this nice property. For every vertex V, it has n most n minus 1 neighbors in these cycles. So now D minus B, this part is just 2n colorable. Okay, so V has most n minus 1 neighbors in the previous cycles, and Ci itself is a n degenerate. D minus B is 2n colorable. And this part, because B induces a bipartite digraph, is 2 colorable. So therefore, D is 4n colorable. Okay. Actually, this approach works for general case. If we consider a cycle tree, first we take one cycle and let it just be a root. Then cycle tree consists of maximal cycle path from R. So in this case, it has 3 maximal cycle paths starting from R. 1, 2, 3. Okay, and then we were able to extend the concept of bad edges. So actually we were able to find the set of external edges of T, of D, such that the most important thing is this, B prime induced bipartite digraph. So yeah, it induces a bipartite digraph, and B prime contains every bad edge of Pi. So it contains every bad edge of this maximal cycle path, every bad edge of this cycle path, and every bad edges of this cycle path. And also, B prime contains every external edge is not contained in the same maximal cycle path. So if we remove B prime from D, then we can color these digraph griddily. Okay? We start with coloring R, and then color this cycle, and then this cycle, and so on. Okay? Because we remove every bad edges, if possible. And yeah, because B prime induces a bipartite digraph, so its chromatic number is n most 2, and this chromatic number is n most 2n. So we have this bound. Okay, this is what we want to prove. Okay, let me finish with some related questions. So actually, our theorem shows that every digraph D has chromatic number n most 8n squared. But the original problem asking if such a digraph has chromatic number n most n. So my question is this. Can you improve this approach to get this bound? Okay. So in our proof, we were able to just prove that it has squared bound, but can you reduce it to linear bound? But I don't know. And recently, in the recent paper, Cohen, Havel, Roche, and Lopez introduced these two objects, K spin and P plus Q bispins. They are kind of generalizations of two black cycles. So two black cycles consists of two maximal directed paths. Here, K spindle is digraphed like this, so consisting of K maximal directed path starting from one vertex to other vertex. And P plus Q bispindle is like this. So it has P directed path from here to there, and Q directed path from here to there. And also in this paper, they show that there exists a strong digraph with large chromatic number, but not containing 3 spindle and 2 plus 1 or 2 plus 2 bispindle. And so only the remaining object is 2 plus 1 bispindle, and they raised this question. Thus, there exists C such that every strong digraph D not containing any subdivision of S has chromatin number bounded by C. Okay, that's it. Thank you.
All right, are there any questions for Ringi?
So all these things talk about strong digraphs. What are they called strong?
Yes. Actually, there is a theorem of where okay. So there is a known example that the digraphs have large chromatin number, but not containing any two black cycle.
So there is an example?
There is an example. Yeah. So
Sorry, there is not, or
there is exist. Yes. So if you consider B black cycle, which means that oriented cycle consisting of a maximal B directed cycle, and there is also known that there exists some digraph with large chromatin number, but not containing any B black cycle. So we only consider strong digraph.